Hi, and welcome to this short introduction to tribotesting. I'm Roland Larsson. I'm a professor or tribology professor at Luleå University of Technology. I will briefly describe the aims for tribotesting here. I will talk about different setups for tribotests and different tribometers. And I will discuss what to do with the results later, how to do the post-analysis of the worn or surfaces after the tribotest. Starting then with the aim of tribotesting. Well, of course, you want to learn about the different tribological processes. You want to understand how the different operating conditions are influencing the tribological behavior and to characterize that behavior. And you want to compare the performance of different materials and lubricants. That is maybe the most typical way of using tribotests. If you want to compare two materials, for example, to see, or two lubricants to see which one is performing best. And in general, you need to mimic the tribological application you are aiming for in the tribotest. I'm coming back to that. That's in general, it's very difficult to mimic the tribological application in tribotest, but still, you have to try to do that. I want to remind you about the different levels of testing. This is not only for tribology, it's in general a problem with testing, but let's focus on tribotesting in this case, and let's use a car as an example. The best would, of course, be to use a field test. You use the car, you run it around on the road or under different operating conditions for years and or hours and years, and then you can disassemble the car and see the wear of various components. That will be, of course, an extremely time-consuming process, and it will not be efficient in any way, really. You will hardly understand how the wear is influenced by different parameters. So in the other end of the scale, then you have a kind of model test. It's the tribotest. Here it's a pin on disc. You have a pin here and the disc. You rotate the disc and you simply see the wear of the pin and the disc, and then you make the pin and the disc of materials that are describing the tribocouple that you want to study in the car here. So that's the lowest level of testing. Next level is a kind of simplified component test. For example, if you have this should show a piston ring, for example, in the engine in contact with a cylinder liner material, and you can run just that tribocouple in a well-controlled test. Of course, then you can't mimic the engine and environment and the real engine kind of conditions, but so that would be better to make a test of the whole component, of the whole system of the crankshaft and the piston and the cylinder line and the piston rings here. Or even better, you run it in an engine test. You operate the engine fully with, then you have the exhaust gases, you have all the vibrations, you have the temperatures, exactly as it is in the real engine, in the real case. Even better is if you can put the engine into the car and run the car in a bench test. Then you also see the interaction of the engine with the rest of the car, or eventually then, as I said, the field test. So the cost is increasing if you go this time, and but the realism is also increasing in this time. The cost goes down in this case, and you also the control of the conditions in the contact. On the other hand, you you may not be able to mimic all the real conditions as you have in the field test in this tribotest. But the thing here, the success factor is of course to be able to understand the model test to understand how the model test links to the field test as good as possible. And that's a trick you have to learn over many years of experience being a tribologist. As I already mentioned, a tribotest must mimic the real application as well as possible. And what does that mean? Well, it means that you have many parameters to mimic. For example, well, maybe the most obvious are the first ones here. For example, the load you apply, or actually the contact pressure you apply, the speeds you apply, the temperatures you operate it in, the time you do the test. It's no point in doing a test in 1 minute when you are going to study a system that will operate in years, for example. You should have the type of motion in a similar way. Is it a rolling or sliding contact? Is it a reciprocating test, or is it a unidirectional? Is it a point contact, line contact, or whatever geometry you have of the surfaces in contact, because that determines the contact pressure. Surface roughness must be the same as in the real application. Also, what is moving? Is one of the surfaces moving or both the surfaces moving in the real system? That is also important to take into account. How is wear debris removed? Do they fall? Will gravity help to take away the wear debris or not? How is it lubricated? You must use the same lubrication, same formulation, same regime of lubrication, of course. You can't operate it in boundary lubrication when you know that the real application operates in full film, or vice versa. Are there any vibrations there? Are there fields like magnetics or electric fields? What is the environment? As I said in the previous example with the engine, inside the engine you have exhaust gases causing another environment if you just run the experiment in open air, and many other things that depends on the application. So this is a very important thing when you design your experiment or your tribotest. Some typical tribotest configurations then, which you normally find in a tribotest lab, are the following. So in the first one here is the pin on disc, and you may have a pin, you may have a specimen that has some geometry. It's good to have a spherical geometry, because then you have good control of the contact spot. Well, to some extent, I will come back to that later. And this is a unidirectional experiment, because the disk is rotating with constant speed, so you have the same sliding speed all the time. Another typical experiment is the reciprocating or oscillating type of test. Then you still have the pin, and you may have a spherical pin like this one, but you move it back and forth. The engine test with a piston ring in contact with the cylinder liner is a test of that type, and that's reasonable since the engine operates in that way. There are a number of other applications where you have oscillating conditions also, but this type of test is also used for general testing of a material pair, even if the real application doesn't have the oscillating motion. And finally, the third, maybe, which is also very common, is the rolling sliding test. In many cases, many machine elements you want to mimic, you have two cylindrical or spherical surfaces in contact with another similar surface. They may roll in contact, or one surface may operate at slightly higher or lower velocity than the other one. So you have partly sliding, so you have a rolling sliding experiment. So these are three typical configurations. This is a picture from a ball on disk test, which is this is from an equipment named WAM, W-A-M. It's Wedevan Associates Machines. It's an American equipment, and here you can see that you have you have the ball here on a spindle, and you have a disc here, so you can. There is one motor running the disc here, and there's another motor running the ball here. And by doing that, you can create a rolling or rolling sliding contact, which is a little bit the same as in a bearing, rolling element bearing, or in a gearbox. So what do you get from a tribotest? These are some figures I found from Jens Hardell's thesis at Luleå University of Technology. And here he has measured the coefficient of friction versus time. This is a very typical type of tribotest. You measure over pretty many minutes, you measure the friction, and you test a number of materials here. So you can see here that in this case the friction coefficient is very high because it was a high temperature experiment. But from the behavior here you can see that, for example, the blue case here, it varies very much with time, while the red one is more constant, and the dotted line here, it's actually the friction goes down with time. So from a test like this, you may find out what happened here. Why was it constant in one case? Why was it changing in another experiment? And actually I was wrong. This was room temperature and this was high temperature. So you can also compare two temperatures. So even if this is a model test, you can learn a lot about the material pair behavior under various test conditions. So what then? Okay, you have measured the friction, and you have seen that it varies, but still you need to try to explain that in some way, and then the post-mortem analysis come into action here. So this is a very important part. You have a whole palette of instruments that you can use here, like material science type of instruments. Tribologists are also using profilometry very much. I mean, the surface roughness measurement. You measure the surface roughness before and after. Well, by doing that, you can see how the surface has changed, if you have created a wear scar and the depth of the wear scar, etc. Hardness measurements could also be before and after, see how the material's properties have changed. And then you have a number of, as I said, the material science instruments, SEM with various tools inside. You can see if you have some materials present on the surface. For example, if you have some concentration of materials in certain parts of the contact, it will help you to understand or explain the processes. AFM is also used. It's more a physics tool, but that's a way to measure the surface roughness or surface topography in more detail before and after the experiment. It could also be used as a tribo experiment itself. You measure the friction in the contact between a tiny tip and a specimen. XRD, then you can measure a little bit the microstructure and of the material or the crystallinity of the material. NMR can help you to learn what's on the surfaces. IR techniques, the same Raman techniques and atomic absorption techniques that is also very good if you want to know what's on the surface after the tribotests. So this is this is a big toolbox, a very expensive toolbox, I would say. Also, most labs they don't have access to all these techniques at the same time, but it's normally required in order to get in-depth understanding about what has happened in the tribo contact. In a tribo lab, you may use optical profilometry as an important tool, as I mentioned, because that can be used for wear assessment. So if you're able to measure the surface before and after, or if you can see where the wear has taken place, you can do a graph like this from a topography measurement. You know that you have surface here that is unaffected by the tribological action. Then you can see that here is the wear scar, and then you can determine the amount of wear. So even if this is nanometers here, you see, so it's less than a micrometer. So one way to do it is to use the optical profilometry to measure the amount of wear. Another way to do it is to weigh the sample before and after. That's maybe the traditional way to do it, but this is a more exact way to do it, because sometimes the wear is so small that it's very difficult to see the difference in weight before and after. This is a nice example, quite recent, of studying the same surface patch before and after. So if you do that, which is pretty difficult because it's not easy to find exactly the same spot of your component or your test samples before and after, but if you can do that, you can directly learn what happened to the surface. And so in this case, this is the new surface, and so the red spots means high peaks, the blue spots means steep valleys, and the yellow is in between. And you can see here that it hasn't changed very much in the valleys, of course, but some of the peaks have been removed, and this is a distribution of the peaks. So you can see that in the post surface there are a little bit more, it's a little bit less points in red, and they have been moved to the more orange and yellow here. So that means that the highest peaks are worn off, and that's natural, of course, during running in, which this is a running in experiment. SEM is a very strong tool for tribologists, or especially material tribologists. This is another PhD thesis from LTU showing a cross-section of a layers formed during the tribological action. And from that, you can also learn then how the microstructure have changed, for example. And again, remember, I have said that before this in the video about the predictions of wear. You must remember that if you have a wear test, for example, a sphere in contact with a flat surface, like the pin on disc configuration I mentioned before, you don't really have a sphere in contact with a disc after some time. Very soon, if I run this is a simulation, starting with a Hertz contact at a gigapascal level, very soon the pressure goes down because of the wear of the sphere or of the disc that flattens the contact, and the pressure will then go down dramatically. It goes down to, say, 0.1 gigapascal instead of 1 gigapascal. So originally, when you say that you run your experiment at 1 gigapascal, you actually run your experiment at 0.1 gigapascal. So it's important to remember that when you compare it to the real application. So to conclude, tribotesting is very complex. This is something you need to gain experience of over a long time, and you need pretty much specific equipment. You need equipment to do the actual motion, to do the actual tribotest, but you also need equipment for the post-mortem analysis. Much of those equipment are very expensive, so it's you really need a lab equipped with machines, $100 million or so in total. It's crazy if you want to do it very, very, very accurately and very on an advanced level. But of course, you don't need to have $100 million machines available. You can still have a pin on disc equipment and measure the friction over time, and from that, and just study the surfaces in a microscope. Then you can learn something from that too. So there is of course a scale from relatively cheap to very, very, very expensive. You should also do many tests, because it's not very accurate tests, and there are many stochastic phenomena taking place, especially when you have fatigue. When you do the fatigue testing, then you really need to do, say, 30 tests of the same in order to learn how the statistics are giving you a distribution of the service life, for example. So being a tribologist, an experimental tribologist, a tribotesting tribologist, you really need to be a kind of detective and pathologist in the same person, because this is since you can't be inside the tribo interface when wear takes place, when friction takes place, you must study it afterwards. You must do this post-mortem analysis normally. So if you think you are a detective and a good pathologist, this is something for you. So that's it about a very short introduction to tribotesting. I'm sure that you can find additional knowledge elsewhere. Thank you very much.